Okay, so as I was saying, thermochemistry is an important area which basically deals with energy changes in chemical reactions. So let me bring the PowerPoint up. Okay, so full screen. All right, so that's what thermochemistry is all about. So before we get into the actual topic, we have to cover some fundamental terms. First of which is energy. What do we mean by this term, energy? Well, energy is the capacity to do work. And when we talk about doing work, what that means basically is if work is applied to an object, that means that you apply force to an object and the object moves, all right? So if I'm pushing like this mouse a certain distance, then I've just done work on it. And therefore, that work will be converted to the energy that the object will have compared to what it was before. So energy, I don't remember where the root word comes from, but basically when translated, it literally means work within. However, you need to recognize that an object does not contain work. Now, as far as the different classification of energy, there are two main types. You have what is known as potential energy, which is the energy an object has by virtue of its position or composition. And then you have kinetic energy, which is the energy that an object has by virtue of its motion, all right? And there's a formula that we can use to calculate the kinetic energy of an object, and that is given right here. The kinetic energy is equal to half mv squared, where let me get this thing together. Okay, what's going on here? And let me get back here. Okay, so in this equation, oops, M would be in kilograms. The units of mass would be kilograms, and the unit of velocity would be meters per second, right? So if you plug these units into this formula, then the resulting unit for energy would be kilograms meter squared over second squared. And that collection of units is basically regarded as the joule unit, or J, right? That's a symbol, right? So the joule unit is the same thing as kilogram meter squared per second squared. So let me go to the next slide. So some other basic terms that you need to be aware of when it comes to thermochemistry. Well, that's the definition, actually, as I said before. It's basically the study of energy changes that will take place in chemical reactions. Now, some terms you have to be aware of that you need to know. Whenever we're talking about a system, we're basically talking about a part of the universe being studied. So basically, that could be any part of the universe. It could be a test tube where the reaction is taking place, or it could be a beaker, or it could be a huge tank. It doesn't matter, right? If you're studying that particular area of the universe, then that area of the universe is called the system. The surroundings would be the rest of the universe, right? So, and also, I want to say, and you're going to see this shortly, that there's always some interplay or interchange that takes place between the system and surroundings that we have to take into consideration. Now, when it comes to systems, there are three types of systems, right? You have what is known as the open system, where you can have the exchange of energy and matter between the system and the surroundings. You can also have what is known as a closed system, where you can have energy being exchanged between the system and surroundings, but not matter. And then you have the extreme case of an isolated system where there's no exchange possible between the system and the surroundings of matter or energy. All right, so that's the difference between those three systems. So the example that is shown here is a jar of honey, which is sealed here. So therefore, this is an example of a closed system because there's no exchange between what's inside the jar and outside, but it is allowable for energy to pass through the walls of the jar to get into the jar or vice versa. All right. So therefore, this is called a closed system, right? Now, here's a question here. If you were to unscrew the lid of the jar, then what kind of system would you expect this to be? Anybody?
Open.
Exactly. It would be an open system. All right. Okay. So some other terms that you need to be aware of: internal energy. That's the total energy that is contained within a system, right? Now, part of the internal energy is kinetic, and it has to do with molecular motion. And when it comes to molecular motions, there are three types. You have translational, rotational, and vibrational motion. And collectively, these are sometimes called thermal energy. And the reason why is because the motions of the type that we just described is related to temperature, right? If you increase the temperature of a substance, then you increase the level and the energy of the motions described, the translational, rotational, and vibrational, all right? The other part of the internal energy is the potential energy, and this is due to the intramolecular and intermolecular forces of attraction and locations of atoms and their bonds, right? So we call these energies the intermolecular and intramolecular forces. We call them collectively chemical energy, all right? So that's basically what internal energy is. Another term you need to be aware of is heat, right? Technically speaking, heat is not energy, but basically, heat is the energy transfer between the system and surroundings, which is caused by a temperature difference. All right. So if you have two objects that are in contact with each other, one is hotter than the other one, then basically you're going to have the transfer of heat from the substance which has a higher temperature to the one with the lower temperature. All right. And the example that is shown here on the right is an example of two gases. One is argon and the other one is nitrogen, right? And there is a very thin hypothetical wall, which basically allows for the energy to be transferred from one side to the other, right? Now, in this particular setup here, the argon is more energetic than the nitrogen, right? So therefore, the net heat transfer would be from the argon to the nitrogen, right? From the system here to the nitrogen in the surroundings, all right? Now, that heat transfer will continue until you reach a state of what is known as thermal equilibrium. Thermal equilibrium is basically where the temperatures of both the nitrogen and the argon are the same. When that happens, then there's no more heat transfer. All right? Now, here's a question being asked right here. How do the root mean squared speeds of argon and nitrogen molecules compare at the point of thermal equilibrium? All right? Now, if you remember, we said that the root mean squared speed, whoops, the root mean squared speed is proportional to 1 over the square root of the molar mass of the particular gas. Now, let me get out of this because I'm going to need some space here to actually work this problem. So let me get out of this and let me get to a Word document. Okay, so basically what we're going to do is compare the root mean squared speeds of both nitrogen and what's the other gas? Argon. Okay. So remember we said that the root mean squared speed. Okay, what is going on here? The root mean squared speed is directly proportional to 1 over the molar mass, right? So basically, if we do this squared is equal to not squared. If we do this for nitrogen, right, this would be, oh, I'm sorry. If we divide the root mean squared speed of nitrogen by that of argon, then that would be equal to 1 over, or not 1 over, but the square root of the molar mass of argon divided by the molar mass of nitrogen, all right? So basically, if you want to compare these two, we have to look at the molar masses of argon. In fact, we have to look it up in the periodic table, which I think is 40 point something. Molar mass calculator to the rescue. Argon. Okay, 39.95. All right, so this would be the square root of 39.95 AMU divided by the molar mass of nitrogen, which is 2 times 14.01, which would be 28.02. All right, AMU. And then we do the number crunching, where we divide 39.98 by 28.02, and then we find the square root. So this would be equal to 1.195. So therefore, the root mean squared speed of nitrogen would be equal to, hold on 1 minute. Okay, so the root mean squared speed of nitrogen would be equal to the root mean squared speed of argon multiplied by 1.195. So therefore, the nitrogen on average would be moving at a greater speed compared to the average argon atom. So basically, to answer this question, the nitrogen will move faster than the argon atom to this extent, 1.195, right? And that's basically it as far as answering that question is concerned. Okay, so let me get back to the PowerPoint and let's talk about work. We mentioned work before, and I think I mentioned that work is said to be done when you push an object or pull an object or apply force on an object and the object moves, right? And in so doing, when you perform work on anything, then basically you'll be transferring energy from the surroundings to that particular system, all right? Now, the difference between heat and work is the fact that work is caused by a force moving through a distance, while heat is caused by a temperature difference, right? And what you're going to see in this chapter, especially when it comes to this specific topic, is that you have to pay attention to the signs, right, that are associated with the value of work and energy and other terms, right? So, for example, if you have a negative quantity of work, what that means is that the system is losing energy. And therefore, what that means basically is that the system is doing work against the surroundings, all right? So that's what happens if the value of work is negative. If it is positive, what that means is that the system gains work, which would mean that the surroundings is basically doing work on the system. All right. So that's basically how we interpret these signs when it comes to work being done by the system or work being done on the system. Please remember, however, that even though you might have negative and positive signs associated with the value of work, there's no such thing as negative energy or positive energy. So basically the sign indicates the energy flow, all right? So with regards to the system, if it is positive, that means the system is gaining energy, which means that work is done on the system or it's absorbing heat. And then if work has a negative sign or if energy has a negative sign, that means that the system is doing work or the system is losing heat. All right, so just to give you an example of how this works. So this is purely hypothetical, not really based in any actual reality, but we can use this to help us to understand the interplay between work and energy and so on for a system. So we have this gas here trapped in this vessel, and you have this plate right here, which is movable, and we're going to assume that it moves freely without any friction occurring, right? So basically, we have the gas here, which has an initial value for the volume, right? And let's say that the gas expands from here to here, right? That means there's going to be a change in volume, and that change in volume would be represented by delta V. So to calculate the work done on the gas, that would be equal to this equation right here, minus P, where P is the pressure, and we're assuming that the pressure is constant. I should say that. We're assuming that the pressure is constant. So therefore, the work done on the gas would be equal to minus P times delta V, which is a change in volume, right? Now, if the volume is increasing, in other words, if the gas is expanding, that means that delta V, that means that delta V would be greater than zero if the gas is expanding, all right? So if delta V is equal to zero, that means that the work calculated here would be less than zero or negative, all right? Because delta V is positive, P is always going to be positive. There's no such thing as negative pressure. And therefore, work would be equal to minus P times delta V, which means that work is negative. If work is negative, that means that the system is doing work on the surroundings, all right? And what that also means is that the system is losing energy, therefore losing energy, all right? So because the system is doing work against the surroundings, that means energy has been expended by the system, and therefore it will lose energy, all right? So that's basically the relationship between work and energy in this particular system where you have a gas undergoing expansion, right? Now, I should put here if delta V is greater than zero, right? Now, let me just continue down here because I don't think I have it on the next slide. If delta V is less than zero, that means that the work would be positive. So what that means is that the surrounding is doing work on the system, all right? Which means that, which means that, therefore, energy is increasing for the system, all right? Okay, so that's basically how we interpret, the different signs and, the type of energy loss or gain based on whether or not you're expanding or compressing the gas. All right, so next slide. State functions. Let me get rid of this here. So that's another term that you need to be aware of. What do we mean by state function? It's well, firstly, you have to talk about the state, right? Now, in everyday language, or probably based on what you would have learned earlier in your, let's say, introductory chemistry, you learned about the three states of matter, right? Solid, liquid, and gas, all right? However, the term state, strictly speaking, is more than just that, right? It's basically referring to the exact condition of a particular system at a particular instant, all right? So just to give you an example or two, let's say, for example, you have iron metal. Let's say you have iron metal at 25 degrees Celsius, and then you heat it to get the same iron metal at 55 degrees Celsius, all right? By virtue of the fact that the temperature is changed, what you have done is changed the state of iron, right? Even though it's still iron, the metal, but because the temperature is changed, that means that the state is changed. Let me give you another example. Let's say you have hydrogen gas at 1 atmosphere, and then you change the pressure of hydrogen gas to 0.25 atmospheres, right? Again, believe it or not, that is also a change in state because you're changing the pressure, right? So that's basically what we mean by the state of a system. Basically, it's condition at a particular instant. Now, let me see what next. Okay, so I stated here, let me clear this. The state is dependent on several things, right? Including the kind and amounts of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature. So the examples I showed you basically illustrate that particular point. If you change the pressure, you're changing the state. If you change the temperature, you're changing the state. Now, a state function is a quantity that has a unique value that depends on the current state of the system. And very important, it does not depend on how the state was arrived, all right? So in other words, it doesn't matter where the state or the history of the system, when it gets to a particular state, then that would be represented by a particular state function, all right? And whoops. And now we're going to talk about the first law of thermodynamics, also known as the law of conservation of energy. And basically what this law says is that in a physical or chemical change, energy can be exchanged between the system and the surroundings, but no energy can be created or destroyed. All right? So that's the first law of thermodynamics. There are actually 3 laws of thermodynamics. The other 2 you'll be introduced to in general chemistry 2, if you have to do general chemistry 2. And also in physics as well, if you have to do physics, I'm quite sure you're going to encounter these laws of thermodynamics. So the first law of thermodynamics can simply be summarized into this statement. Energy cannot be created or destroyed, but you have to be careful because you have to say, in addition to that, that this is referring to physical or chemical processes. And the reason why I mention that is because this is not true for nuclear reactions, right? You can have energy created from matter and vice versa, all right? So this is strictly with respect to chemical and physical processes, right? Now, one conclusion you can come to is that when it comes to internal energy of a system, that is simply the difference between the energy between its final and initial state, all right? So I think I have an equation here which represents that. Delta U, which is the change in internal energy, is equal to the internal energy in the final state minus the internal energy in the initial state. And let me just say that this particular arrangement, final minus initial, is true for every change in a particular quantity that you're going to encounter in this chapter, because later on, we're going to look at, for example, changes in enthalpy, right? Or changes in temperature even, right? In any case, it's always the final value minus the initial value, all right? So as you see in this case, the change in internal energy is the final internal energy value minus the initial internal energy value, all right? Another additional inference is that the change in internal energy, if it occurs as a result of change in heat or work, then this is the relationship between the change in internal energy, heat change, and the amount of work that is done on the system, all right? So that's the relationship between delta U, Q, and W, all right? Now, again, I can't emphasize this enough. It's very important that you pay attention to the sign for these different quantities, right? Now, in the case of energy entering the system, the change in internal energy is going to be positive in that case, right? And that change can be due to one or the other of these two. Heat absorbed by the system and work done on the system. So if you have a system and it absorbs heat from the surroundings, or if you do work on a system, both of those will result in a positive change in energy of the system. And then the opposite is true if heat is lost by the system or the system is doing work on the surroundings. In those two instances, the sign of the energy associated with those changes will be negative, which indicates that overall the system is losing energy. All right. So very important for you to pay attention to the signs, especially when it comes to solving problems such as this one right here. Now let's pay attention to how this question is worded. Before I do that, let me remind you of the equation. Let me write it up here. The equation is delta U is equal to Q plus W. And by the way, let me just say this. In some textbooks, you'll see that instead of using U, they use the letter E. So this could be represented as delta E, all right? But in your textbook, if I'm not mistaken, they use delta U, all right? So delta U is equal to Q plus W. Okay, so let's see if we can apply this to solving the problem here. Again, you have to read the question carefully because interpreting the question carefully would result in you having the correct signs for the different quantities. So the question says, a gas does 135 joules of work. Let me highlight that here. While expanding, and at the same time, it absorbs 156 joules of heat. So the question is asking, what's the change in internal energy? So this begs the question, what's the value of Q based on the information provided, right? Now, notice the question says that the system absorbs 156 joules of heat, right? What that tells you, of course, is that the heat change is positive. So this will be plus 156 joules, right? And then now for this part where it says the gas does 135 joules of work, what that means is that work is equal to minus 135 joules, right? Because the system is doing work on the surroundings. So therefore, we plug these numbers into this equation. Delta U is equal to Q, which is 156 joules, minus 135 joules, and 21 joules would be the answer. All right? Okay, any questions about this? Any questions? There's one question, and I forgot to bring the assignments. I'm getting old. I forgot to bring assignment 7 today. But there's one question in the assignment. In fact, let me bring it up on the screen here. Let me go here.
Do you mean assignment 6? Because I think was last one we.
I mean, assignment 6. You're right. Yeah, assignment 6. Okay, files. Assignment 6. I'm going to publish it so that you can have it to look at. And actually, there are 2 links. This link as well. Okay, so going back to 6 here. And let me clear this. Oh, shoot, I clicked the wrong one. Okay, this is the question I'm referring to, right? It says, calculate the total change in internal energy They use delta E there, but remember we said that delta U is also used to represent that. Of a system, when 400 joules of heat is applied to expanding oxygen and the gas does 350 joules of work on its surrounding, all right? So again, let me remind you that the equation is delta U is equal to Q plus W, right? So based on how the question is worded, what is Q equal to? What's Q equal to?
400.
400 joules or plus 400 joules. And what is W equal to?
350.
350, but look here. It says the gas does.
Oh, it does it on the surrounding, so negative 350.
Exactly, minus 350. Right? So delta U in this case would be equal to plus 400 joules minus 350 joules, which would be equal to 50 joules. And that's it. All right? Any questions about this? Any questions? Okay, so let me clear this here. Oh, let's do this question, actually. We should be able to do this question. This question is asking for us to calculate the kinetic energy in joules of a particle, well, joules, calories, and kilojoules of a particle. They gave the mass of the particle, which is 9.11 times 10 to the minus 28 grams, and they gave us the speed of this particle as well. So remember the formula I gave you is kinetic energy is equal to half mv squared, right? So basically, it's a matter of putting the numbers into this equation, but we have to be careful here because remember I said that the mass here must be in kilograms. They gave us the mass here in grams. So what I would do first to calculate the kinetic energy is convert the 9.11 times 10 to the minus 28 grams to kilograms.
Isn't velocity in meters per second?
Yeah. So I'm going to multiply by 1 kilogram over 1,000 grams, all right? And then, as he correctly said, the velocity is in meters per second, but according to the formula, you have to square it. So you're going to multiply by 6.00 times 10 to the 5 meters per second, and then we square that, and then we work that out. So 9.11 divided by 1,000, and then multiply by 6 times 10 to the 5 squared. And, ooh, is that right? Let me do this again. 9.11 times 10 to the minus 28 divided by 1,000 times 6 times 10 to the...
Don't you have to times it by 1/2?
Oh, right. Thank you. So 6 raised to times 10 to the 5 squared multiplied by 0.5. So according to my calculation, this works out to be 1.63 times 10 to the minus 19. And this would be in joules. So we have determined the energy in joules. To convert that to kilojoules, we multiply this by 1 kilojoule above and 1,000 joules below. So the joule units will cancel out, and this works out to be
1.63 times 10 to the negative 21, or 22.
22, yeah, 1.63 times 10 to the negative 22. And this would be in kilojoules. And then to convert this to calories, this would be given in the table, the relationship between the calorie unit and the joule unit. 1 calorie is equal to 4.184 joules. So basically, let me just erase some of this stuff here. So 1 calorie is equal to this. So I would take the 1.63 times 10 to the minus 19 joules and multiply it by 1 calorie over 4.184 joules. And let's see what that gives. Divided by 4.184. So according to my calculation, I'm going to roll it off to 3 sig figs. So the answer I got is 3.90 times 10 to the minus 20 calories. And that's basically how that is done. All right? Any questions? All right. Back to the PowerPoint. Let me clear this first. Okay, so let's move to the next slide. Okay, now heats of reaction. Let's define that term. The heat of a reaction is basically the amount of heat that is exchanged between a reaction system and its surroundings, right? And basically, with regards to energy changes or heat changes in a reaction, there are two types of reactions, right? Or two categories of reaction defined by the heat changes occurring. We have what is known as an exothermic reaction, right? In which case the reaction gives off heat. And in an isolated system, the resulting mixture, whatever that is, its temperature will increase. And as a result of the system going from a higher energy state to a lower energy state. All right? So that's what we mean by an exothermic reaction. An example of this would be if you were to add sodium hydroxide to water, right? So let's say you have a test tube and you add a few granules of sodium hydroxide to the water and you stir it. After a time, if you feel the outside of the test tube is going to feel warm or even hot, depending on how much of the sodium hydroxide you would have added. So that would be an example. It's not really a reaction per se, but it's an exothermic process, right? When sodium hydroxide dissolves in water, right? So basically generates heat as a result of that. Now, the opposite of exothermic reactions would be endothermic reactions. And in the case of endothermic reactions, as the reaction progresses, what this system will do is absorb heat. So therefore, if you were to do that reaction in a beaker or a test tube, for example, if you add sodium nitrate to water in a test tube or beaker, and you feel the outside of it is going to feel cold or cool, depending again on the amount of sodium nitrate you would have added to it, right? So as stated here, it absorbs heat. When you feel the coldness, that's heat being absorbed from your hand, all right? So in an isolated system, the temperature decreases and the system will go from a lower to a higher energy state, which means that Q reaction, which is the heat of reaction, is positive. All right? So exothermic means that Q reaction is negative. Endothermic means that Q reaction or the heat of reaction is positive. And to illustrate this point, let's look at this these three containers of, I think they call, I think it's, well, I'm not sure what it is. But anyway, you have a reaction taking place in each case, right? Now, let's look at the extreme left. The extreme left is a purely hypothetical situation because basically what they're suggesting is that if this is an exothermic reaction, which is what is stated above here, then any heat that is generated will immediately escape the container and be absorbed by the surroundings. Problem is that this is not realistic. There's always some heat generated in an exothermic reaction, but not all of it will be released to the surroundings. What is more likely to happen, oh, by the way, so basically in this case here, the temperature would not change from what it was before. So if the temperature is 25 degrees Celsius and you have the heat just escaping without being absorbed by whatever is left in the vessel, then the temperature will remain at 25 degrees because after all, according to this here, the surroundings are 25 degrees, right? So therefore, the temperature for the apparatus set up to the extreme left will not be possible, all right? And the temperature remains the same. Now, in the case of the second one, which is more likely to happen, some of the heat will escape into the surroundings, but some heat will be absorbed by what is remaining in the vessel. So as a result of that, the temperature is going to increase from 25 degrees to 32.2 degrees, all right? So this is what happens in real life, all right? Basically what happens is that some of the heat is absorbed by what is left, but the rest of the heat basically escapes as well, but not as much as in the case of the first example, right? So that's what happens in the middle setup. Now, in the final setup, we have an isolated system. Styrofoam cups are very insulating because they do not allow any heat to pass through. So this is a closed system also because it is covered, right? So in this particular case, if you carry out the same exothermic reaction in this setup right here, where you have two styrofoam cups, then basically the temperature will rise even further. Whoops, sorry. Compared to this one here. So as you can see here, the temperature rose to 35.4 degrees Celsius, right? And that's because when the reaction takes place, it's exothermic, it generates heat, but the heat is not allowed to escape through the walls of the container. So basically, it's a solution, whatever is left there, will absorb the heat that is generated in this reaction, all right? Now, if you understood all of what I've said with respect to exothermic reaction, then you should be able to interpret and predict what would happen in each case if the reaction is endothermic. So I'm not going to get into that right now. I'm going to leave you to ponder that and come to your conclusions, all right? Okay, so that's as far as this specific exothermic reaction is concerned. So let's talk about using the same equation, which is delta U. Where is, oh. Okay, so the equation we're looking at is delta U is equal to Q plus W, right? That's what we're looking at here, right? Now, let's talk about a situation where the reaction is carried out at a constant volume, right? Now, let me remind you that work is equal to minus P delta V, right? So if delta V is 0, right, because it's at a constant volume, that means that W will be equal to 0 because W is equal to P minus P times delta V. If W is equal to 0, that means that this equation simplifies to delta U is equal to Q, all right? So that's basically what happens in the case of a constant volume situation, all right? So as stated here, delta U is equal to Q, which we can represent as QV, where V is a subscript, which indicates that the volume is constant, right? So the diagram that you see here on the right is showing you what happens under those conditions, right? If the volume remains constant, then basically any heat energy that is over a particular value will escape in the particular chemical change. But in this particular case, if the volume is constant, then basically delta U is equal to QV, all right? So basically there's no expansion. That's why it says here no PV work is done, right? So basically it just sits at that volume and gives off heat, which would be equal to the change in internal energy, right? So the heat given off would be equal to the change in internal energy, which is the case for this situation where the volume is held constant. Now, the other situation, which I think is what is on the next slide, is where the pressure is constant. Let me just get rid of all of this here. Now, going back to the equation I showed you, right? Let me ask you this. How many of you have done calculus? Okay.
Like Cal 1 or?
Cal 1, yeah. You?
I'm in breakout.
Oh, okay. All right. So I'm just going to go into this. Hopefully you'll be able to grasp it. So basically what we're looking at here is delta U, sorry. Okay, so going back to this equation, delta U is equal to Q plus W, right? And we said that W is equal to minus P delta V in this situation, right? Which means that, oh, 1 minute. Well, all right. Which means that, which means that delta U is equal to Q minus P delta V, all right? So now, let me just explain something, and this is where the calculus may come in. I'm just going to do it here. In actual fact, delta U would be equal to Q minus delta, the product of PV, all right? Now, this here would be equal to Q minus delta PV plus P delta V, right? Now, if delta P is equal to 0, that means that delta U will now be equal to Q minus P delta V. I'm just showing you this to show you how we get this equation right here, right? And you can rearrange it, as you can see here, to get an expression for QP, which is equal to delta U plus P delta V, all right? So that's what happens under constant pressure conditions. And let me just say this. Most reactions are done under constant pressure conditions, right? Constant volume conditions are more difficult to arrange. So therefore, most reactions that you'll encounter will not, cannot be predicted in terms of, changes in energy and so on by the previous equation that I showed you, which was delta U is equal to QV, right? Most reactions will be under constant pressure conditions. So therefore, this equation will apply. QP is equal to delta U plus P delta V. Okay, now let me erase this here because, okay, so basically, in the case of a constant pressure conditions where you have a reaction taking place, most of the energy is released as heat, all right? And then some work is done to expand the system against the surroundings, right? So what you're saying here is that delta U is equal to QP minus P delta V. This here is the work part, this here is the heat part of that equation, right? So that brings us now to another term, enthalpy, and enthalpy change, which is related to it. The definition of enthalpy is given here. Delta H, I'm sorry, H is equal to U plus P times V, all right? So if you want to find out what QP is, which is the change in heat under constant pressure conditions, QP would be equal to delta U, I'm sorry, this thing is not cooperating today. Okay, delta U plus P delta V, right? Because again, as I was saying before, delta H would be equal to delta U plus delta PV, right? And delta P plus, not plus, I'm sorry, delta PV here would be equal to, let me continue down here, delta H would be equal to delta U plus P delta V plus V delta P. And because it's constant pressure, this would be equal to 0. So therefore, this equation is the equation for under constant pressure conditions. So the QP here is basically the change in enthalpy, right? And the change in enthalpy is a measurable quantity. It can also be calculated if you have other measured quantities. And we're going to get more into that later on. But I want to show you this diagram right here, which shows you the reaction between magnesium and hydrochloric acid. Very exothermic reaction produces a gas, so therefore the gas will expand against the surroundings. So therefore this equation would apply as far as this reaction is concerned. All right. Okay, so so as stated here, most reactions occur at constant pressure. So therefore, for most reactions, the heat evolved equals the enthalpy change. All right. Okay, so that's as far as that's concerned. So let us look at some properties of enthalpy, because this will become important when it comes to problem-solving exercises. The first thing we're going to say here is that enthalpy is an extensive property. What does that mean? That means that the magnitude of the enthalpy is dependent on the amount of reactants involved in a reaction, right? Another thing you need to understand is that enthalpy is a state function. It is a state function because it is a function of other state functions, such as the internal energy, pressure, and volume. And then basically enthalpy changes have unique values, all right? But of course, that would equal to the heat change under constant pressure conditions, right? So as stated here, going back to state function properties of enthalpy, enthalpy change depends only on the initial and final states. And that's true for every state function. It's always final minus initial when it comes to calculating the change of that particular quantity. Now, let's talk about some more about enthalpy changes. We can determine the values of the enthalpy changes experimentally, right? In fact, and I probably should have included it here, you cannot, in practice, determine enthalpy based on determining the absolute values of internal energy, all right? So basically, you can just determine delta H by experiments or by doing certain calculations, which you're going to see later on, with experimentally determined values. Okay, now, if you have a negative enthalpy value, that means that the reaction is exothermic, which means it's losing heat energy. If the enthalpy change is positive, then that reaction is endothermic. And that is illustrated by these two diagrams right here. In this case here, the reaction is exothermic because as you go from reactants to products, heat is lost, energy is lost, right? So the energy of the products will be less than the energy of the reactants. So if you were to find the enthalpy of the products and the reactants, then delta H will be equal to enthalpy of products minus the enthalpy of the reactants, and that would be a negative answer, right? As shown here, right? This is indicating that delta H is negative. On the other hand, in the case of an endothermic reaction, the products will have a higher energy compared to the reactants, right? So in that case here, again, it's always the final minus the initial. So because the products have a higher enthalpy compared to the reactants, that means that the resulting difference between those two, products minus reactants, would be equal to delta H, which is positive, all right? So that's basically how we can explain enthalpy changes graphically. So let me see here. Okay. So what happens if you were to reverse a reaction? What happens to the enthalpy? Well, basically what happens is that the sign will change. So in other words, if you have a reaction, let's say, for example, mercury oxide forming mercury and oxygen, that's an endothermic reaction, right? Here's the value of delta H for that reaction. So the reverse reaction would be basically, quantitatively speaking, the value of delta H would be the same, but negative, right? So basically, if you turn the reaction around or reverse the reaction, the enthalpy change would be the opposite in terms of sign compared to what it was before, all right? That's very important too, as you're going to see. Again, we apply this to solving certain problems. What time is it? Okay, 1220. All right. So let's look at these examples right here. Let's start off with the first one. The first one says, given the equation, and it gives you the equation, and it gives you the delta H value, calculate delta H for the reaction, and it gives you the second equation. Now, my question to you is this. I want you to look at those two equations and ask me, or tell me, what's the difference between them? And I'll give you a hint. There are two differences I'm looking for when you compare these two. What's the difference between the first equation and the second equation? And there are two hints. There are two differences. I'm sorry. Two differences.
The amount of substance used.
What do you mean by that?
Like in the first equation, you're getting 2 moles of HI, where in the second, you're only getting 1 mole of it.
Okay. That's partially true. What I was looking for in reference to what you're saying is that the difference between the first one and the second one is that all the coefficients in the second one will be half of the coefficients respectively for the first one, right? So in the case of H2, here, right, the coefficient is 1. Here it's half. I2 has a coefficient of 1. Here it's half. HI, has a coefficient of 2, but here it's 1, right? So that's one difference, right? But there's another difference. What's the other difference?
The first one is a synthesis reaction, and the second one is a decomposition reaction, so they're reversed.
Okay, it's reversed. Right, exactly. So basically, the second equation is the reverse of the first equation. So what that means is that the products of the first equation would be the reactants in the second equation and vice versa, right? So the question now becomes, how do those two changes as you go from one equation to the other affect the delta H value? Well, let's take it in steps, right? Now, we mentioned first that the coefficients are halved, right? So what that means is that if you were to have all the coefficients for this equation here, so I'm just going to multiply by half, then the equation becomes half H2 gas plus half I2 solid to give HI gas. All right? So the question now is, what will be the effect on delta H by having everything? And the answer is that if you have all the coefficients here, you have to divide that by 2 as well. So the delta H for this reaction will be half of plus 52.96 kilojoules, right? And that would be equal to what? 52.96 divided by 2. So 26.48 kilojoules, right? So if you have all the coefficients here, you have to divide this by 2, and that will be the result. Now, the next thing we have to ask ourselves is, how do we get from here to here? How do we get from this equation to this equation right here? And again, we talked about the fact that we need to flip the equation so that the reactants become the products and vice versa. So the question now becomes, what would be the consequence of flipping the equation on the delta H value that we just calculated here? And the answer is that this is positive. So when you flip the equation, this value becomes negative. So therefore, delta H for this equation will now be minus 26.48 kilojoules. All right? And that will be the answer. Okay, any questions about this? Any questions? Any questions? Okay, so the next example. Now I'm going to need some space for this one. So what am I going to do? I'm going to clear this first. And what I'm going to do is copy and paste this onto a Word document. Okay, so let me go to, where's the Word? Oh, Word is here. So let me lasso this here. And let me paste. Okay, so that's a question. It says the complete combustion of octane liquid octane, I should say, to produce gaseous carbon dioxide and liquid water at 25 degrees Celsius and at a constant pressure of, oh, I'm sorry, at a constant pressure gives off 47.9 kilojoules of heat per gram of octane. Write a chemical equation to represent this information. Now, to be fair to you guys, the question, I know what the question is asking for, but it didn't express it clearly. What the question is asking for is not just the equation, right? But it's also asking for the delta H value for the balance equation, right? So the first thing we need to do in order to answer this question is
Balance
Right.
the
write a
equation.
balance equation, right? So based on the information provided, what would be the reactants? Based on the information provided, what would be the reactants on the left side of the equation?
H.
C8,
C8, H18
plus
plus
O2.
O2. Very good. What would be the products on the right side of this equation?
CO2 gas,
CO2 gas plus
H2O.
H2O liquid. All right. And by the way, O2 is a gas here, and the octane is a liquid here. Okay, very good. And then we need to balance it. Okay, so how do we balance it?
It has to be at least 8 carbon dioxide,
Okay,
and then there has to be at least 9 H2Os.
okay. I would agree with that.
Just have to balance the O2.
How
So,
would you do that?
It's not correct as is. We need to change the coefficients because we have a
you have,
odd number of H2O.
Hmm?
Or we have an odd number of oxygen. We would have
So 16 plus 9, that's 25, right? So what I would do is put a 25 over 2 here, right? And then I'll multiply everything by 2. So the final answer, well, not the final answer, but for the equation is going to be 2C8H18 plus 25O2 to give 16 CO2 plus 18 H2O. All right, so that would be the equation that you're going to work with, right? Now let's look at some other things the question has provided. And again, it's very important that you pay attention to the wording because of this part of the question. It says that when the combustion takes place, it gives off 47.9 kilojoules of heat per gram of the, oops. Okay, why did that happen? I want to draw a circle around it. So this is basically what I was pointing to. It gives off 47.9 kilojoules of heat per gram of octane, right? So basically what the question is asking for you to do is to determine delta H for this equation, right? So this is the octane right here. What I would do to solve this problem, I would start off with 2 moles of octane, since we have 2 as a coefficient of octane, right? And then what I would do next is convert that to grams. So you're going to have 1 mole of C8H18, and I'm going to go to my trusty calculator. C8H18, and what does that give? 114.23. So that number would go down here, 114.23 grams of octane. And then the next step,
would that be vice versa?
oh, I'm sorry. Yeah, you're right. My bad. So that would be 114.23 above. Thank you very much for correcting me on that. And then 1 mole of octane below. All right. Okay. So the next step would be to, okay, so where we, oh, this is where this comes in, right? So remember now it says gives off. Gives off tells you what about the sign? of the heat that is expressed there. If it is giving off that much heat, that means the sign is what? Anybody?
It's negative.
Negative, exactly. So you're going to put minus 47.9 kilojoules. And down here, I'm going to put 1 gram of C8H18, right? And that would give us the amount of heat change that will occur in this case. So that's 2 times 114.23 multiplied by 47.9 minus, and if I were to run this off to 3 sig figs, the answer would be minus 1.09 times 10 to the 4 kilojoules. Kilojoules. All right? And that's it. That's how you solve that problem. All right? Any questions about this? Any questions? Okay, let's see what next is up. Okay, so when it comes to doing certain calculations, we can involve enthalpy values as if they are chemicals for the sole purpose of doing the calculations of the type that we're going to meet later on. So as you can see, having a balanced equation to begin with is very important. So you'll have to make sure that that is in place first. And then what you can do is generate conversion factors, which relates the amount of heat change occurring with certain amounts of the different substances. So for example, in this case here, in the case of this reaction, the reaction between hydrogen and chlorine to form hydrogen chloride, and they gave you the delta H value here, right? Then basically you can write down relationships, for example, between the enthalpy change and the moles of hydrogen. That would be given by this, or you can flip it. It all depends on the type of calculation that you're trying to achieve. You can do the same thing here for chlorine, and you can do the same thing here for the hydrogen chloride, all right? So you're going to see how all of this works when it comes to doing certain calculations. In fact, let's do this one. I think this is going to be the last thing we're going to discuss. So they gave you the equation, and they gave you the enthalpy change, right? And the question is asking, what's the enthalpy change associated with the formation of 5.6 moles of HCl? So what I'll do is start off with the 5.67 moles of HCl, and I'll multiply by the appropriate conversion factor, where the denominator is where the denominator is actually 2 moles of HCl, and the numerator would be minus 184.6 kilojoules. And that's it. This will go with this, and then you do your calculation, and that would be 5.67 times 184.6 minus divided by 2, and according to my calculation, this works out to, when rounded off to 3 sig figs, 523 kilojoules, and that's it. All right? So that's basically how that is done. Okay, I'm going to stop here because I think the next topic would be, let me see here. Okay, yeah, I don't want to get into that and stop in the middle of it. That's calorimetry. All right, so before you leave, I'm quite sure you have seen the announcement, but I'll remind you anyway, I won't be here on Friday, all right? Not for class and not for office hours, okay? Because I'll be going out of town for a meeting, all right? Test number 2 will be next week, this time, all right? And it's going to be based on chapters 3, 4, and 5, right? I haven't graded chapter 5 yet. I'm going to get started on it today, and then I'll send it to you graded as soon as possible. But in the meantime, I've posted the answer key for that chapter, right? So you can review that chapter using the answer key in preparation for your test. I've given you back your graded assignments 3 and 4. You can also review those for your test as well. All right. And if you have any questions, of course, while you're studying for that test, please feel free to contact me during my office hours. All right. So that's basically all I have by way of announcements. All right. So I'll see you guys next Wednesday. All right. Okay, and for you guys out there in